Okay, so in this lecture, we are going to start the arithmetical logic circuits. And I just told you that there are different arithmetical logic circuit. Those could be like addition, subtraction, multiplication, division, complement. So these all are like incremental, decremental circuits. So these all are the some of the arithmetical logic. And one of the arithmetical logic is the binary adder. Okay, so let us try to see what binary adder is and how it works. Basically, binary adder means if we are adding two digits, two bits, then those kind of circuits, we can call them the binary adder circuits. Okay, so like suppose I have to add 0 0 0 1 and 0 1 0 1. Suppose I have two numbers and I want to add these two numbers. So what we are doing here, we are doing each digit with the pair, like whatever the here 1 and 1, that will be added. So 1 and 1, if I will add 1 and 1, I will get 0, and 1 carry will be forwarded to this one. So because on this operation, what I did, I consider one here and one here, and we added these two digits. Okay, so for this purpose, we need some binary adder circuits. But now if we see, if I have started adding from the LSB, so initially I do not have any carry that had come from here and there. Okay, so for that purpose, I need to add only 2 bits. But if other than LSB, there is a high chance that I will get some carry forwarded from the previous bit. Okay, just we can see this combination. In this combination, I have this 0 that I need to add with this 0, but there was one this one which was carried forward from here. So might be for the first operation, I need a circuit that can add, let us assume I have A and B, and that can give you the sum, and maybe that can generate some carry. So this kind of logic circuit is needed for the LSB side. Okay, but this circuit cannot fulfill your requirement if you are moving other than the LSB. Might be you need one circuit which can add two numbers A and B, but that also need required one addition of the carry input that is coming from the previous bit. Okay, and the output of this circuit should be, again, there should be sum and there should be some carry. Okay, there is a high chance that you will get some output, and then you also need to get some carry that can again be forwarded to the next MSB. Okay, so for this operation, we need the binary adder. So if you're talking about only 2-bit addition, okay, so these kind of circuits, we can call them the half adder circuit. Why half adder circuit? So this circuit, whatever I just explained here, this circuit is nothing but this is the half adder circuit. So we can call them the half adder circuit. Why half adder? We are not considering the previous carry. We are only considering the current input that I have to add. That is why we can call them the half adder. But if you see the second case, in the second case, we are considering the current input as well as the carry generated from the previous bit. Okay, so we are also considering the carry from the previous bit. So we can call them the full adder. So this is the difference between half adder and the full adder. So basically there are two kind of binary adders. The first one is half adder and the second one is the full adder. In half adder, we are considering only the current bits which we have to add. We are not considering the previous carry that has been generated. But in the full adder, we also need to consider the previous carry. Okay, so this is the difference between half adder and the full adder. And this is how we need adder to perform any of the addition operation. Like, yeah, just I explain you how we can do that. Okay, so let us start with the half adder. Okay, so I just told you in the half adder I can have only 2 inputs. Okay, I don't need to consider any of the previous carry, and here I will get 2 inputs, X and Y, and I will get 2 outputs like sum and carry. Okay, and if sum and carries are there, then we can have this kind of 2 input and 2 output possibilities. Okay, so if I have this kind of possibilities, then let us try to make the truth table. 0 0 0 1 1 0 1 1. Now can anyone tell me what will be the sum table? If I am adding 0 plus 0, then the sum will be 0. 0 plus 1, sum will be 1. 1 plus 0, sum will be 1. Yeah, so again let us try to see, because if I am adding 0 plus 0, 0 plus 1, 1 plus 0, there is no carry that was generated. Okay, so there is no carry. But if we talk about the last case, 1 plus 1, that used to give 0 and carry is generated, so carry will become 1 here. So this is the truth table for the half adder. Okay, so now if we try to write the expression like the sum function, that is, this is the function of x and y, can be written as summation of minterms 1 and 2. Similarly, carry can be, carry xy is nothing but summation of minterm. Yeah, we have only one minterm, so that will be 3. Okay, so this is how we can write the sum and the carry. Now, because we know this sum and carry, so let us try to simplify this circuit. Okay, yeah, directly we can see this looks like a which kind of circuit we need for this purpose. Directly you can see this is the truth table of
XOR.
XOR 1. And what is that? And what about this one? This is the truth table of
AND gate.
AND gate. So directly by seeing this circuit, we can say, but because the variables are very less, only 2 inputs are there. Okay, so we need one XOR gate for this purpose and one AND gate for this purpose. Okay, but if the more number of variables, you cannot directly see like what kind of circuit is needed. So you need to solve this one. Okay, so let us try to solve those things. Okay, so let us try to solve for the sum. For sum, I have 1 and 2. So 1 is here and 2 is here. Okay, and for carry, I have only 3 that is given here. Okay, now try to solve it. Okay, so the sum is equal to, if you see this one, this is nothing but, this is giving x y bar plus this one is giving x bar y. Okay, and we know that x y bar plus x bar y, this is nothing but x XORing y. So this is what the sum term is. Similarly, if we talk about the carry one, so again I cannot make the carry pair with anyone. So the carry can directly be written as a into b. Okay, so let us try to make the circuit. For carry, we need 2 inputs x and y. Okay, and we need one AND gate. And for sum, we need one XOR gate that will be connected with x and y, and that will give you the sum. So this is how the half adder circuit will look like. Okay, so this was quite simple because we have only 2 inputs and 2 outputs. But as we increase more number of input, like suppose I have 3 inputs, in that case I will get 8 number of total possible combinations. So we cannot directly predict by seeing the truth table. In that case, definitely you have to design those things. So this is required actually. Okay, for a smaller circuit, you can directly see and you can pick any of the logic gate to design the circuit. But for the bigger one, if the function is complex, in that case, the direct pick and connection is not possible. Like so in that case, you have to design by this way. So the procedure will be like this only, whether the function is small or function is complex. This is the simple procedure. What you have to do, you have to write all the combinations for the input, whatever we have written over here. Then based on the combination or based on the requirement, I have to prepare the truth table for the output, and then I have to solve the k-map for total number of outputs whatever we have, because in this case I have 2 outputs, so I need to solve the k-map for 2 outputs, sum and carry. And then based on the solution, we need to design the circuit. So this is the procedure which we have to follow for all the logic circuits, whatever we will consider later on. Okay. So let us, so this is the procedure. Now, suppose I have to design a half header. We have seen here. If we see here in this half header, we have designed this circuit based on the AND gate and the XOR gate. But suppose if I want to design the same circuit with the help of NAND gate, then how we can do that? Okay, so let us try to see that one. Okay, so let us start with the sum expression in the carry expression. We know that sum is given by, if we can recall, we had x y bar plus x bar y. If we see here, if I want to implement this particular function, in that case, I need, how many logic gates are needed to implement this function? Can anyone tell me? Suppose I want to implement this one, and not just using the XOR gate, with the help of normal logic gates, then how many logic gates are needed?
5.
Someone is saying 3, someone is saying 5. Any other options? Okay, so let us try to see here. We need one AND gate for this purpose. We need one AND gate for this purpose, and we need one OR gate for this purpose. But we need two inverters for Y bar and X bar as well. So total number of gates are 5. Okay, so the who said 5? This is absolutely correct. So the total number of gates or the logic gates that are needed to implement this function is the 5. Okay. Now let us try to, because the question is like I have to design a half header with the help of NAND gate only. So I have to convert this expression that can give you the expression something like A, B complement. This is the simple function of the NAND gate. Okay. So I need to convert all the terms, whatever present here, like this, A plus B complement form. Okay, so that I can use it as like I can use the NAND gate to implement that function. So let us try to see that one, how we can do that. For that purpose, I need to use simply the Boolean function, whatever we have used before, or the Boolean law, which we have done it before. So let us try to see it. Suppose I have this function, okay, and if somehow I am adding x bar, so there is no problem. X bar is always 0. Okay, plus x y bar, which we have already here, then I am adding x bar y plus y bar. So if I have this kind of expression, this is same as the previous one, it will not create any problem, but that will help you to simplify this one. How it will help you to simplify? From first two term, if I take out the x as a common, I will get x bar plus y bar. And in the second term, if I take y as a common, so I'm again getting x bar plus y bar. Okay. Now, if I apply the De Morgan's theorem over here, okay, because I need the terms like this, A plus B bar. Okay. So because A bar plus B bar, like if the function is like this, I can also write this like A bar plus B bar. Okay. So I need to convert this one like x into x y bar plus y into x y bar. Okay. Now, what other process that we can follow? Can anyone tell me how we can simplify? Yeah, we got this term as a NAND, this term as a NAND, but what others? What we can do? What is the procedure that we can follow? Can anyone tell me? Okay. So let us try to see it. Because if I have to apply the De Morgan theorem, the complement on the function is required. Okay, so because see, we do not have the complement at the top. Okay, so if I want to remove this plus symbol, there should be a complement at over here. Okay, so to do that, what we can do, I cannot simply put a single complement. So in that case, what I can do, I can use xy bar plus y xy complement, and I can put two complement over here, and that will not create a problem. But this complement will help you to remove this plus symbol. Okay, so how we can solve this one? Let us try to see here. If this is the term, so what I will get? I will get the expression something like x into x y bar whole bar into y x y whole bar and then complement and then whole complement. So this is how we can simplify it. Now let us try to see. There is no plus symbol anywhere, and we are getting the sufficient complement term to solve it. If you see the outermost part, like this is the term, this is the term, and this is the complement, that will give you the NAND. Okay, now let us go into the somewhat lower hierarchy. If you see in this one, this is the term, this is the term, and we are getting one complement over here, so that will make you the NAND gate. Okay, so this is also possible. Now if you see here, we are getting xy bar, so again this is just like a NAND gate. So now we are able to get the exact requirement whatever we have. Now let us talk about the carry. Okay, suppose I have a carry, and carry is nothing but this is x into y. Okay,
हेलो सर.
yeah, please.
सर सम में यदि अपन एक्स वाई बार कॉमन ले लें तो फिर एक्स प्लस वाई आ जाएगा होल स्क्वायर
At which state?
इन फोर्थ लाइन में सर
For
एक्स
here,
वाई बार
yeah,
कॉमन
what?
ले लें.
Yeah, x y complement, so we'll get x plus y. Yeah,
Yes.
yeah.
और
So
सर एक्स प्लस वाई को सर एक्स बार वाई बार का होल बार लिख सकते हैं ना.
yes, of course that can be done. Yes, yeah. So x by what the bar, and then you can you're saying like x bar
वाई बार
bar.
नो सर
Nah, okay. You're saying like bar then bar. Okay, x plus y complement and complement. Yes. Okay, so you're applying x y bar, and
नो
then you
सर
will apply De Morgan's theorem like x bar dot y bar and whole complement.
यस
Okay,
सर.
then yeah. So what you need yeah, this is doable. This is also doable. For that purpose, to generate x complement, you need one inverter. So for that purpose, you can use AND gate as an inverter as well, NAND gate as an inverter. So this is used, and this can also be, yeah, this is also possible, no problem at all. So this is correct way. This is also one of the way that you can do it. So see, whatever I just told you, this is not the way, but there could be another way as well, right? So here what you can do, you need one inverter for x bar, you need one inverter for x bar, and we know that from NAND gate you can make one inverter. Okay, and whatever the inverter we are getting, that we have to pass through a NAND gate, and that will give you this particular function, the second function. Okay, but the problem is again, you are getting the first term and the second term, which are in terms of ending, not the NANDing. So you have to complement it 2 times. So what you need two complement. 2 complements means the x by complement, then x complement dot y complement, then whole complement, then 2 complements. Okay, so this is what you can do. You can use one NAND gate, and again you need to pass it through one inverter to make this complement. Okay, so you need to check how many gates are needed. Okay, so can anyone tell you how tell me like how many NAND gates are needed to implement this function and to implement this function? How many NAND gates are needed to implement both the functions? Yeah, both are possible. There is no problem. But I need number of gates requirement.
Sir, 4.
4 in the first case?
Sir, second.
In the second case, you are saying 4. Okay. Any other?
First one is also 4.
First one also required 4. Okay, let us try to check how many gates are needed. If you see here, we need one gate for this one, which is the XY bar. Okay, so this is first. Okay, so this XY bar can be utilized for this purpose as well. Okay, second one is needed this with X. So the second gate is needed for this purpose. Okay, third one is needed for this purpose. Okay, you don't need to use XY bar 2 times. The single gate can give you the logic. Okay, so that you can utilize it again. Okay, so first here, second here, third here, and fourth here. Okay, so this is what the first gate is required. Now if you talk about the second one, so 4 is absolutely correct for the first one. Now let's talk about the second case. In the second case, you need one here, one you need to complement it, one you need to complement this one you need to simplify this function, one you need to simplify this function with this one, and one you need to find the complement. So you need total 6 number of gates now. If you see the second case, in the second case you need total 6 gates. Point is clear? So the gates in the second case, like gate requirement in the second case is 6, not the 4. Okay, because we have to consider X bar and Y bar as well, because we have only one inputs X, Y. Okay, and I have to make all the requirement whatever we have. So for that purpose, you need because you have to design with the AND gate only, NAND gate only. So to make the inverter, you have to use NAND gate again. So the total number of NAND gate requirement in the second case will be 6, not 4. Point is clear? Any doubt on this? Anyone?
Earlier we say that if XY is available, then XY and Y bar is also available. So we will consider that point, or we will not consider while designing the
Okay,
gate.
so you consider that thing again, but see, while calculating the exact requirement, yeah, that is absolutely correct that X and Y is present, then X, Y, and Y is also present. But suppose I have to make a black box where I have only 2 inputs X and Y and 2 outputs. Suppose I'm talking about half header. So half header is not like I have 4 inputs. Half header has only 2 inputs. Like it's not like X bar, X bar, and Y and Y bar. So it is not like this. The half header circuit is not like this. The half header circuit is like this only. And if it is like this, so I have to consider only 2 input and 2 output. And based on that, to invert the logic, we again need inverter inside this one. Okay, inverter is needed inside the black box. Okay. So because we are designing half header, we are not designing a general circuit, because in half header 2 inputs and 2 outputs are there. Okay. So you got the point what I'm saying?
Yes, sir.
Okay. So this is how we need 6 number of gates. Yeah, for general purpose, X bar and X both are present. But because our application is to design half header, and in half header only 2 inputs are there, so you need to convert to complement the X and Y as well. Okay. So this is how it looks like. Yeah, I was thinking to finish many part, but unable to do that. No problem. Okay, so suppose I have carry, which is the X and Y. So can anyone tell me how I can make this with the help of NAND gate? How I can generate this carry with the help of NAND gate? This is the AND one.
Double AND.
Okay, so what I need to use simply X, Y bar and then bar, right?
Yes, sir.
So I need X, Y bar, that will give you the NAND gate, and then I have to again use one inverter that with the help of NAND gate, and that will give you the carry. Okay, so this is what we can do. Now let us try to implement this logic circuit. Now I have one more question. Suppose as of now we got from this term we need 4 number of NAND gate, right? And if we try to implement this one, you need 2 number of NAND gate. So can anyone tell me how many number of NAND gates are needed to make a full adder, a half adder?
So 5.
5. Okay. Any other opinion? 5 is absolutely correct, because if you see inside the half adder block, we already have X, Y bar. If we already have X, Y bar, so we do not use to implement again this X, Y bar. So I can use this X, Y bar, which is available over here, and then I have to pass it through an inverter and we will get the carry. Okay, so this is doable. So the total number of, it looks like we need 4 for this and 2 for this one. No, we need total number of 5 NAND gate to design the half adder with the help of NAND gate. Okay, fine. So let us try to, based on this analysis, let us try to design this circuit. So the first circuit that why I need X, Y bar, because this term is we are using 3 times. One is here, one is here, and one is here. Okay, so we are using X, Y bar 3 times. So we need to first make X, Y bar. Okay, then what I have to do? I have to find this one, that I have to NAND with X and whatever the X, Y bar we have. So this term is nothing but this is the X, Y bar. Okay, I have to NAND it again with the help of X. So at this point, I will get X into X, Y bar whole bar. Okay, so this is the term which I will get here. Similarly, here I will get Y into X, Y bar whole bar. Okay, so this is the output which I will get. Now what I have to do, I have to again pass these 2 inputs, whatever I have, through a NAND gate. Okay, so that I can make the sum term. So this is how I will get it. So this is what the sum term is. Okay, this is the sum. Now if we talk about the carry, so because we already have this X, Y bar over here, so I need to just simply complement it through an inverter and I will get the carry. Okay, so this is how the circuit looks like. So this module, what we can say, this module is the XOR one and this module is the AND one. Okay, yeah, we also solve one problem here, like how to design the, previously we tried to design the XOR and XNOR logic with the help of universal gates, but I directly made the logics. I directly made the circuit how it looks like. But now from this justification, you can see how we can design the XOR gate with the help of NAND gate. The similar kind of approach will be applied if you are using the NAND gate, NOR gate. Okay, with the help of NOR gate, you can also design the XOR and XNOR gate and other things. So this is also possible. Okay, so one thing we also finished over here, that how to design the XOR with the help of NAND gate.